This video delves into the invisibility principle that makes stealth aircraft unique, exploring the underlying technologies, challenges, and the future of stealth innovation. From radar-deflecting shapes to heat-dampening materials, we uncover how these marvels of engineering achieve their near-mythical status on the battlefield. Understanding the invisibility principle. The invisibility principle in stealth aircraft is a groundbreaking concept that aims to make these machines as undetectable as possible. 1. The goal of the invisibility principle. The primary objective of the invisibility principle is to minimize the aircraft's visibility to enemy detection systems. This is achieved by reducing the signature of the aircraft across various detection methods, including radar detection, the most common form of surveillance, which uses radio waves to identify objects. Infrared detection, sensors that track the heat emissions of an aircraft. Acoustic detection, devices that pick up noise produced by engines or airflow. Visual detection, the simplest form of detection using eyesight or cameras. By addressing these detection methods, stealth aircraft can operate with a significant tactical advantage. 2. Key detection systems and countermeasures. To understand the invisibility principle, it is essential to examine the detection systems it counters and the corresponding stealth strategies. Radar cross-section, RCS reduction. Radar systems work by bouncing radio waves off objects and detecting the reflected signals. Stealth aircraft reduce their radar signature by designing angular, flat surfaces that deflect radar waves away from the source, using radar-absorbent materials that absorb rather than reflect radar signals. Infrared signature management. Infrared sensors detect heat emissions from aircraft engines. To counter this, stealth aircraft employ advanced cooling systems. Exhaust designs disperse heat over a larger area, making detection harder. Acoustic suppression, aircraft noise caused by engines and airflow can be detected by sound sensors. Stealth technologies mitigate this by designing quieter jet engines, optimizing airflow to reduce turbulence and noise. Visual camouflage. Visual detection relies on sight or optical sensors. Aircraft minimize their visual signature by using special paints and materials that blend with the sky or ground, exploring adaptive camouflage that changes to match surroundings. 3. The role of integration in stealth. Stealth is not achieved through a single feature, but a combination of integrated systems that work harmoniously. Design, shaped to reduce radar visibility while maintaining aerodynamics. Materials, advanced composites and coatings reduce both radar and thermal signatures. Systems, electronic warfare tools actively jam enemy radar and communication systems to avoid detection. Through these sophisticated techniques, the invisibility principle ensures that stealth aircraft remain one step ahead of evolving detection technologies. Technological foundations of stealth. The technological foundations of stealth are rooted in advanced engineering and material science, enabling stealth aircraft to minimize their detectability across multiple spectrums. These technologies collectively work to reduce radar cross-section, infrared emissions, acoustic noise, and visual signatures, creating an intricate balance between functionality and invisibility. 1. Radar cross-section, RCS. Reduction radar systems detect objects by bouncing radio waves off surfaces and interpreting the reflected signals. Reducing RCS is a cornerstone of stealth technology, achieved through two main approaches. Aircraft shaping. The unique angular and faceted shapes of stealth aircraft, such as the B-2 Spirit and F-117 Nighthawk, are designed to deflect radar waves away from the source, preventing their return to radar receivers. Features include sharp edges and flat surfaces, avoidance of protruding components like antennas that could reflect signals. Radar-absorbent materials, RAM. Special coatings and materials absorb radar waves instead of reflecting them. Carbon-based composites and polymers are commonly used. RAM converts radar energy into heat, which dissipates harmlessly. 2. Infrared, IR, signature management. Infrared sensors detect heat emitted by engines and surfaces. To counteract this, heat-dampening technologies, advanced engine designs minimize heat output. Heat exchangers and cooling systems disperse or redirect exhaust heat. Infrared suppressive coatings. Surface treatments reduce heat reflection and emission. Exhaust redirection. Engine exhaust is cooled and spread out over a larger area before release, lowering its visibility to infrared sensors. 3. Acoustic suppression. The noise generated by an aircraft's engines and airflow can be tracked by sound detection systems. Stealth aircraft incorporate quieter engines, turbofan engines with advanced sound dampening designs, optimized aerodynamics, reduction of airflow turbulence around the aircraft, noise-absorbing materials, sound-absorbing materials used in the fuselage to dampen vibrations and engine noise. Number 4. Visual camouflage. Stealth aircraft must also minimize their visual signature to evade human sight and optical systems. Low observable paints. Dark matte finishes reduce glare and visibility against the sky. Specialized coatings reflect minimal light, blending with various environments. Adaptive camouflage. Experimental technologies include dynamic surfaces that change color or pattern to match surroundings. Nighttime operations. Preference for missions under cover of darkness when visibility is naturally reduced. Number 5. Electronic stealth systems. Modern stealth technology integrates advanced electronic systems to actively disrupt enemy detection. Electronic warfare (EW) systems. Jamming devices confuse radar systems or prevent them from locking onto the aircraft. Low probability of intercept (LPI) communications. Secure communication systems emit signals that are difficult to detect or intercept. Active radar cancellation. Technologies that emit counter signals to cancel out radar reflections, effectively making the aircraft invisible to radar. 6. Materials and coatings. The materials used in stealth aircraft play a critical role in reducing their detectability. Composites, lightweight, radar-absorbent, and durable materials form the aircraft structure. Specialized coatings. Coatings that absorb or scatter radar, infrared, and even ultraviolet signals. Stealth technology represents a synergy of these elements, ensuring that stealth aircraft remain undetectable while maintaining operational effectiveness. The constant evolution of these technologies highlights the innovation required to counteract advances in detection methods. Key features of stealth aircraft. 1. Low radar cross-section, RCS. The defining characteristic of stealth aircraft is their ability to minimize radar detection, achieved through angular design. Faceted surfaces and smooth curves deflect radar waves away from their source. Examples: the triangular shape of the F-117 Nighthawk and the blended wing body of the B-2 Spirit. Radar-absorbent materials, RAM. Coatings and structural materials absorb radar waves, preventing reflections, commonly made of carbon composites or ferromagnetic substances. 2. Infrared IR signature suppression. To evade heat-seeking technologies, stealth aircraft employ advanced methods to reduce heat emissions. Engine placement and cooling systems. Engines are buried within the fuselage, and heat is dispersed through cooling vents and exhaust mixers. Exhaust shielding. Engine exhaust is directed above or blended with ambient air to lower thermal visibility. Infrared absorbent coatings, applied to surfaces to minimize heat reflection. 3. Acoustic signature reduction. Noise generated by engines and aerodynamics can betray an aircraft's presence. Stealth aircraft minimize this through quieter engines, low-noise turbofans designed with advanced noise suppression features. Aerodynamic optimization, reduce turbulence around the aircraft's body to lower sound levels. Noise-dampening materials, interior linings and structural components absorb vibrations and sound. 4. Visual camouflage. Stealth aircraft reduce visibility to the naked eye and optical sensors through low reflective coatings. Matte black or gray paints reduce glare and blend with the sky. Blended designs, contours that avoid shadows or sharp outlines to confuse visual observers. Adaptive camouflage, experimental. Technologies under development aim to change surface appearance to match the environment. 5. Electronic countermeasures. Incorporating advanced electronic systems helps stealth aircraft remain undetectable. Low probability of intercept, LPI radar. Radar systems with minimal emissions, difficult to detect by enemy systems. Electronic warfare suites, jamming and spoofing systems that disrupt enemy radar and communication. Data encryption and secure communication, systems designed to emit minimal detectable signals during operations. 6. Composite and advanced materials. The construction of stealth aircraft involves cutting-edge materials that contribute to their stealth capabilities. Lightweight composites, reduce weight while maintaining structural integrity and radar absorption. Multifunctional coatings, absorb radar and infrared signals while providing durability. 7. Weapons integration. Stealth aircraft are designed to carry weapons without compromising their low observable profile. Internal weapons bays. Missiles and bombs are stored inside the fuselage to maintain aerodynamic and radar profiles. Retractable doors. Weapons bay doors open and close quickly to minimize radar exposure during launches. Conclusion: the invisibility principle of stealth aircraft represents a remarkable achievement in modern military technology.